Have you ever stopped and just really thought about Google Maps? I mean, it feels like magic, right? You pull out your phone, ask it for pretty much anything on the planet, and in the blink of an eye, it delivers this perfect interactive replica of the world to guide you. Well, today we're going to pull back the curtain on this incredible feat of engineering.
You know, it all kicks off with something so simple, something we do all the time without even thinking about it. You type in "coffee near me." You just expect an answer, instantly. But what happens in that split second between you hitting enter and that map popping up? Well, it's anything but simple. And that really is the question, isn't it? How does that little request from your phone travel maybe thousands of miles across an ocean to a data center, get processed by this massive system, and then beam a perfect answer right back to your screen in less than a second? So let's do it. Let's follow that single query. We're going to trace its journey from the tip of your finger, through the giant digital brain of Google Maps, and all the way back to that little blue line that you follow on your screen. Okay, first things first, we have to wrap our heads around the sheer scale of this problem. Because this isn't just about finding one coffee shop for you. It's about doing that for basically everyone, everywhere, all at the same time. Google Maps serves over 1 billion. That's billion with a B. Daily active users. 1 billion people asking for directions, looking up businesses, checking traffic. Just engineering a system that can handle that kind of load without completely buckling. That is the first mind-boggling challenge. All right, so before your question can even be answered, Google has to build a digital twin of our planet. And that all starts with collecting just a staggering amount of raw data. Think of this as the world's most intense data cleaning operation. Google is just constantly drinking from a fire hose of information. We're talking satellite images, GPS pings, even user reports about road closures. This whole pipeline takes all that messy, chaotic input and turns it into the clean, reliable map you see. It standardizes formats, gets rid of duplicate info, and fact-checks everything before it ever gets to you. So, you've got an entire planet's worth of data. How do you possibly organize it so you can find anything quickly? You can't just scan the whole globe for every single search. That's where something called spatial indexing comes in. These are basically hyper-efficient digital filing systems. For instance, Quadtrees are awesome for quickly finding what's on the map as you zoom in and out. Hierarchies, on the other hand, are perfect for finding all the restaurants within a specific area you draw on the map. Each one is a specialized tool to find exactly what's needed in milliseconds. Okay, the map is built and organized. Now let's get back to our coffee search. The system has to translate that very human phrase, "coffee near me," into a language computers get. Precise latitude and longitude coordinates. This whole process is called geocoding. The system breaks down what you typed, it cleans it up so it knows ST and street are the same thing, and it searches its databases for matches. But here's the really clever bit, the ranking. It's not just about what's closest. It looks at popularity, business hours, user reviews, all to give you the best result, not just the one that happens to be 10 feet closer. And how is the map actually drawn on your screen? Well, it used to be done with what are called raster tiles. Think of them as tiny little square pictures stitched together. But modern maps use vector tiles. So instead of sending a picture of a road, the server sends the raw data, like the coordinates for the start and end of the road, and instructions on how to draw it. This is a game changer. It means super smooth zooming, it uses way less data, and you can do cool stuff like tilt and rotate the map. It's just way more flexible and efficient. Okay, we've found our coffee shop. Now for what might be the most critical part of all, getting you there. This is the art of routing. And when you're doing it on a global scale, it is a serious computational nightmare. Now, the classic old-school way to do this is with an algorithm called Dijkstra. It works, and it's guaranteed to find the shortest path. But it's a brute force approach. Imagine dropping a pebble in a pond. It explores outwards from your start point in every single possible direction. For a small city map, that's totally fine. But for a cross-country trip? Yeah, on a continental scale, it fails. Spectacularly. Using that method to find a route from New York to LA would take minutes, not the milliseconds we expect. Google Maps needed a much, much smarter shortcut. And here is that brilliant shortcut. It's a technique called contraction hierarchies. Just think about how you plan a long road trip. You don't worry about every single local street along the way, right? You just focus on getting to the nearest major interstate. This algorithm does exactly that. It pre-calculates the most important highway routes, creating these shortcuts that let the search completely skip over millions of tiny little residential roads. And the impact is just staggering. This one optimization is what cuts the routing time from minutes down to milliseconds. It is the secret sauce that makes Google Maps feel instantaneous, even for incredibly long and complex trips. But a perfect route on paper is totally useless if it leads you right into a 5-mile traffic jam. So the final layer of intelligence here is making the map a living, breathing thing that responds to the real world as it changes, second by second.
So, how does Google know about a slowdown? Sometimes before you even see the brake lights ahead. It's basically watching from everywhere. It's aggregating anonymous GPS data from millions of phones, it's combining that with official road sensors, it's factoring in user reports of accidents, and it's even pulling in data from third-party partners. All of this to build an incredibly complete picture of traffic.
All that raw data then gets processed in real time. The system gathers all these signals, it filters out weird anomalies, and then it uses machine learning to actually predict how traffic is going to evolve. Then, and this is the really key part, it updates the map's internal cost for traveling down a certain road. A traffic jam simply makes a road more expensive in terms of time, which forces the routing algorithm to find a cheaper, faster alternative for you.
So we have the data, we have the search, the routing, the real-time updates. Now how on earth do you make this entire complicated system work reliably for a billion people at once?
The philosophy is actually pretty simple. You expect things to break. The entire system is built for failure. Everything is copied and running in multiple data centers all over the globe. So if an entire data center in, say, North America goes offline because of a power cut, your search is seamlessly rerouted to one in Europe or Asia, usually in seconds, and you never even notice anything went wrong.
And this architecture leads to almost unbelievable reliability. We're talking 99.99% uptime. For a service that people genuinely rely on, sometimes in emergencies, that level of dependability isn't just a nice-to-have, it's absolutely essential.
And it's all built on a foundation of data at a scale that is almost impossible to comprehend. We're talking about petabytes, that's thousands of terabytes, of map tiles, imagery, and real-time data streams. Just managing this ocean of information is one of the greatest engineering challenges of our time.
So, what is next for this digital world? Are we going to see directions overlaid directly onto our vision with augmented reality? Or maybe maps that are so precise down to the centimeter that they can safely guide fully self-driving cars? The system is always evolving, and it feels like the line between our physical world and the digital one is only going to get blurrier.